Hello, everybody. We are going to start on the second lesson about rectangle approximation methods. So you should have already watched a video about RRAM, LRAM, and MRAM that got us through one page of notes. And now we are going to the second page of notes. Look at that. So we are going to be here on example 3. You should probably have a calculator nearby. I have mine, and I'll probably be using Desmos on the screen. All right. So what do I got here? Now, one of the questions I always get is, can computers do the area under the curve for us? Why do we have to do the rectangles? That just seems silly to do these rectangles when we could be more specific. And you're right, that's true. But the thing is, you don't always have a graph. Sometimes all you have is data. And if you have data, rectangles are going to be the way to go. So this is an example of what if you don't have a graph? You don't need a graph to estimate the area under the curve. You can use data points as well. So it says, consider the continuous function f of x with values given below. And now I'm going to ask you some questions. Now, some of these have to do with area, some of them don't. And that's what we're going to do right now. So it says, estimate f prime of 3. Well, that has nothing to do with area. Well, here's 3. If I want to estimate the slope at 3, what I want to do is hug the point and find the slope at the end point. So if I want to estimate f prime of 3 can be approximated by figuring out the slope from 4 to 2. F of b minus f of a over b minus a. And so in this case, that's going to be 15 minus 9 over 2. 15 minus 9 is 6. 6 over 2 is 3. There's a great estimate for f prime of 3. Fine. Estimate the area between f of x and the x-axis on the interval from 0 to 12 using LRAM in 3 rectangles. Okay, so I'm going to sketch a graph for a second here. And let's see, if I sketch this graph, and I have to go from 0 to 12, and I have to use 3 rectangles, and it'd look like this. Well, 12 divided by 3 is 4. So this would be 4, 8, and 12. And then if I want to use LRAM, I'm going to draw up from the left end point. So if I bring this thing to the left end point and draw up to the curve, well, let's see, at 0, y equals 4. So that rectangle will go from 0 to 4. My next rectangle is going to start at 4 and is supposed to go all the way up to 15. This is not drawn to scale. And then my last rectangle using LRAM would start at 8. 8 is at 16, so a little bit higher. And it would look like that. So if I want to estimate the area, I could just add up those rectangles. So the base is 4 on all of them. And my heights are 4, 15, and 16. And what I really did is I just did 4 times f of 0 plus f of 4 plus f of 8. And let's see, this is going to be 16 plus 4 is 20. 20 plus 15 is 35. 35 times 4 is 140. Cool. Fine. I'll deal with it. All right. Then it says estimate the area between f of x and the x-axis on the interval from 0 to 12 using RRAM and 4 rectangles. Well, if I use RRAM and 4 rectangles, there's 12. That'd be 6. And cut each of those in half. I'd have 3 and 9. And if I'm using RRAM, I'd find my height at 3, find my height at 6, find my height at 9, and at 12. I'm just sketching these. I did not look at the table. So let me go back and do that appropriately then. Let's see. At 3, let me erase what I have. At 3, my height is 12. So for 3, I'd go up to 12. Fine. For 6, I go all the way to 20. That's bigger. For 9, I'm way back down here at 6. And at 12, I'm back up a little bit at 8. And so if I want to estimate the area between f of x and the x-axis using RRAM and 4 rectangles, all of my widths are 3, and my heights came from f of 3, f of 6, f of 9, and f of 12. So I have 3 times 12 plus 20 plus 6 plus 8. So that's 20, 46. 46 times 3 is 138. Hey, That's pretty close to 140. Cool. And then it says, estimate the area between f of x and the x-axis on the interval from 0 to 12 using MRAM and 6 rectangles. Okay. So if I go from 0 to 12, and if I use 6 rectangles, so that would be at 6, and split each of these into thirds. So I would have 2, 4, 6, 8, 10, and 12. And if I use the midpoint, I would need to use f of 1, f of 3, f of 5, and you get the idea, and so on. All right. So if I'm going to use midpoints, each of my widths are 2, and my heights come from all the odds, f of 1, 3, 5, 7, 9, and 11. Because those would be the midpoints of all the subintervals. And notice, this thing right here is just my entire width divided by the number of rectangles. If my width is 12 and I have 6 rectangles, they'd each be 2 wide, assuming that I am using an equal distribution of subintervals, which I am. All right, so in this case, I have 2 times f of 1, 3, 5, 7, 9, and 11. Let's see, f of 1 plus 3 is going to be 5 plus 12, 9, 18, 19, 18, 6, and 4. 1, 2, 3, 4, 5, 6. All right, so that's 17. 17 plus 19 is 36. 36 plus 18 is 54. 64 times 2 is 128. Okay, I did it. Now, the other question you might want to ask yourself is, which of these is likely the best estimate for the true area under the curve if I were to turn this into a smooth graph? Well, on the front, we said if you want to get a better estimate, use more rectangles. So likely, though not necessarily, but we're going to say likely, D is the best approximation for the true area under the curve. The more rectangles, the closer you should be to reality. All right, so why are we doing this area stuff? What's the point of finding the area under the curve other than, I told you could? Well, when you find the area under the curve, you're multiplying 2 things. You're multiplying the value from the y-axis times a distance on the x-axis. You're multiplying y times delta x. So assume you're driving a car at a constant speed of 45 miles an hour, and you drive for 2 hours. So if you've got your cruise set to 45 and you drive for 2 hours, you've gone 45 times 2, which is 90 miles. What does that mean for a graph? It means, what if your y-axis represents your velocity in miles per hour and your x-axis represents time? If I drive for 2 hours, let's say that's from, hour number 1 to hour number 3, and I'm getting up to speed here, and then I set my cruise at 45 miles per hour. If this is 45, the area under the velocity graph will give you your distance traveled. Technically, it gives you displacement, but if velocity is always positive, it'll get you your distance traveled. So the area under the curve does a lot of what's called accumulation problems, where you say, I'm doing something for a while, how much of it have I done? And you multiply your y value times your x value, and you get it. So here's another example with speed. Remote control car is driving at varying speed as given in the table below. Estimate its distance traveled in the first 5 seconds using RRAM with 5 rectangles. Now, I'm not going to draw a graph this time. We're just going to say, all right, if I have 10 seconds to go and I'm going to use RRAM with 5 rectangles, 10 divided by 5 is 2. So the width of each interval is 2. So I go from 0 to 2, 2 to 4, 4 to 6, 6 to 8, 8 to 10. And if I'm using RRAM, each of the widths is going to be 2, and my heights go from, let's see, f of 2, because that's the right endpoint from 0 to 2, 4, 6, 8, and 10. So 22 plus 5 is 27. plus 11 is 38, plus 2 is 40, plus 0 is still 40. So 2 times 40 is 80. Now let's talk about units. We multiplied 2, which is a change in time, which is in seconds, right? Times velocity, which is in inches per second. So I did 2 seconds times 40 inches per second, which is 80 inches. Then it says estimate the distance in the first 10 seconds using MRAM in 5 rectangles. Well, if I'm going to use MRAM in 5 rectangles, 10 divided by 5 is still 2, so the width of all my rectangles is 2, but between 0 and 2, my midpoint would be 1. So all of my heights for these rectangles would again come from the odds. F of 1, 3, 5, 7, 9. So that's going to be 2 times 12 plus 10 is 22, plus 13 is 35, 41, 47. Hopefully I'm doing that math right there. And let's see, 2 times 47 is going to be 94. So 94 inches. In 10 seconds, it's gone 94 inches. That seems like a remote control car with a dying battery. All right, cool. Estimate the area bound between the graphs of the equations y equals ln x, y equals 0, x equals 4, and x equals 7 using 6 subintervals and the right endpoint method. Is this approximation an over or an under, and why? Okay, well, I'm going to graph this because that seems like a good idea. So if I want to graph y equals ln x, it looks like this. Yes, you should know it looks like that. If you don't know it looks like that, know it now. So there's y equals ln x. And y equals 0 would be the x-axis. And x equals 4 would be like here, because this is 1, by the way. So x equals 4 would be like there. And x equals 7 would be like here. And so I want to find the area in here using 6 subintervals and the right endpoint method. Okay, well, I went from 4 to 7, which is a distance of 3, and I want to use 6 subintervals, so the width of each subinterval is 0.5. Okay, so I can do that. And if I use RRAM, one way to think about RRAM is start from the end and come back. So my widths are 0.5, and my heights come from f of 7, and then go down by a half each time. So 6.5, 6, 5.5, 5, and 4.5. 1, 2, 3, 4, 5, 6. And I didn't use f of 4 because I'm using a right endpoint, and 4 would be the left endpoint. Okay, so that's going to really be 0.5 times the ln of 7 plus the ln of 6.5, and so on and so forth. So I, in my calculator, am going to type that in. You know what? I'll do it on the screen so you can see it too. So on here, bloop, I am going to do 0.5 times the ln of 7 plus the ln of 6.5 plus, plus the ln of 6 plus the ln of 5.5 plus the ln of 5. Uh, 4.5. And I think that's everything. 1, 2, 3, 4, 5, 6. Yes. 5.213.8. 3 decimal places. So I'm going to write 5.213 or 5.214. I decided 5.213. All right. Now, is this an over approximation or an under approximation, and why? Well, let's see. If I draw this as a right endpoint, It looks like it pokes out. But you're not allowed to say this is going to be an over approximation because the rectangles are too big. That's an answer that like a 7th grader should give. When I want an answer from you, we need a calculus answer. So if I look at it, it's obvious that this is going to be an over approximation once you draw it out. But why is it an overestimate? Well, it's an overestimate because the ln function is increasing. And if I'm increasing, then my right endpoint is going to be higher than my left endpoint. So it's an overestimate because the ln function is increasing. Technically, it's because it's increasing on this interval. But technically ln increases everywhere, so you don't really need the parenthetical. Other times you might though, so I'm putting it in there. If a function is increasing on the interval that you're finding the area for, you are guaranteed that RRAM is an overestimate. For the same reason, you would be guaranteed that LRAM is an underestimate. All right, so RRAM and LRAM, their approximation types are based on whether the function is increasing or decreasing. When something is increasing, RRAM is too big. When something is decreasing, LRAM is too big. And I'm done now. So I hope everybody's having a good day. If you have some good jokes, send them to me because I have been out of jokes lately, which really makes me sad. I got to find some good ones or some bad ones so that I can tell them to you. The only joke I have right now, I don't even know if I told this group not. Hey, what's like kind of like blue, but just a little bit, it doesn't weigh as much. Kind of like blue, but it doesn't weigh as much. Light blue. I know, it's so bad. This is why I need good ones from you guys. So have a good day. See you later.